So, when I look at system tuning, tuning means something different to different people depending upon their background and what they're doing. As I said earlier, most people when they're tuning, they're looking at optimizing the program or the code itself. Application tuning. And here they're one-sided, they're only looking at one thing, one application in the system. Again, always fix your application first, optimize it as much as possible. If I'm CPU bound and my 200-second job is taking 2 weeks, I'm not getting any work done and I'm wasting those CPU cycles on barrier synchronization, for example. I'd rather fix that problem than add more CPUs. Okay? So code optimization is what most people do. That's where most of the work is going on. A big issue here is that a lot of the scientific codes out there are still written for Cray vector machines. And the way they nest their loops and stuff like that are designed for vector word processing of the data. And once they move that loop onto a cache-based machine, you have to look at redesigning the way that loop is laid out, how it's nested and the dimensions in the order that you do the dimensions. For example, a three-dimensional array may go X, Y, and those are in sequential strides, but then when you go through the Z dimension, you're pinging through the data such that you're missing everything and you're not able to hold the data in the cache. So on a vector machine, that wasn't a big issue, but on a cache-based machine, it is. So those are the kinds of things that you worry about. And when I get into application tuning, there's a book out on TechPubs on optimization. Unfortunately, to most people, optimization is pure CPU optimization. There's very little on memory and very, very little on I/O. Most people are tuning on the CPU side, reducing their CPU time. Basically trying to get their CPU service time as short as possible. Now the second thing in system tuning is system use optimization. As my systems get bigger and bigger, I'd like to make sure that I'm using it. I'd hate to have a 128 gigabyte machine and only use 2 gigabyte of memory during the whole month. If that memory is there, I can either use it or move it. Okay. The bigger the machine, the more I want to optimize it. A workstation is not so much optimization, it's just survival for the interactive environment. But once you get into larger systems, you want to make sure that the system is properly configured for that workload. And that's something we'll get down to a few more bullets called sizing. Most of the time, the salesman does not size the machine. They come up with a contract based upon how much money the customer says they want to spend. Okay? And they ask no questions about how many people do you intend to log in on? How many people are going to be, how many car crashes do you intend to do concurrently? If it's a web server, what kind of database are you going to run on it? Oracle, or is it video, or what are you doing? So you need to kind of narrow those things down. As I get my system use up and start using the system, then I got to worry about managing it. Again, IRIX does very little scheduling. Most of it is just managing the problem once it occurs. So it doesn't politically say code 2 is more important to me, so I'm not going to steal pages from it. It just says code 2 is the biggest in memory, so I'm going to steal pages from it. And that would be counterproductive. So resource managers kick in simply to say, I've got a problem, but they don't worry about the politics of what to do about it. Then you get into political scheduling. And again, this is where, for example, Army, Navy, Marines all bought the same machine and are sharing it. Where at a university site, we may have physics, chemistry, and astrophysics. They pooled their budgets together to buy the single machine and they want to share it. And political scheduling starts getting into multi-user, multi-group competition. If Army paid for most of the machine, they want to use most of the machine. So with political scheduling, we've got things like batch schedulers. With NQE, I can set up a queue just for Army. And then the people that submit to that queue are in the Army group and they get what they need. I can also set up miser or partition the system, soft or hard partition, and say 32 CPUs would go to Army, 32 CPUs would go to Navy, and the rest can go to anybody that's not in those two particular groups. We also used to have the Fairshare scheduler called Share 2, which was a second generation rewrite of the Share scheduler in Unicos. Now that resource, that product was no longer supported about a year ago. So I no longer cover Share 2, but it was an extremely useful product. Okay. The reason that we didn't support it any further was because of financial contract arrangements weren't financially appropriate with the vendor. I do know of a couple sites that are still running it, and they deal directly with the vendor for that particular code. But past 6.5, I can expect all the support for Share 2 to go away. And I have not heard of any replacement plans for it yet. But Share 2 is an example where I could say you get 50% of the sheet, you get 25% of the sheet, and Word gets 25% of the sheet. And if you all submit work at the same time, the scheduler would decide who gets the CPUs based upon how much you've used versus what percentage of the machine you're entitled to. And that would solve some of the political issues as well.
Who's the vendor for Share 2?
The name of the company changed. It used to be called Softway. Now it's called Aruma, A-U-R-E-M-A. So they kind of commercialized. Same thing happened with PBS, by the way. They used to be called MRJ Technologies, and they got bought up by Veridian, which is why they now have a priced product out there so that they can turn it into a revenue generator. But Aruma, A-U-R-E-M-A, is the present company. And they have a website out there, and I've got documents about using the product. But without a convenient way of getting a license and not supporting it, I can't cover it in the class anymore. But it was something I would normally cover in Unicos. Other political scheduling issues might be file system layouts. For example, Army, Navy, Marines, if they all use the same /temp file system, Army could fill up the file system and Navy can't get any work done. So you may create a /Army, /Navy, /Marines and separate things out. Segregate your I/O traffic. We're going to get into that theme a little bit later. I use the analogy of a moped between semi-trucks. I want to put the mopeds in the moped lane and the semi-trucks in the semi-truck lane. I want to segregate my I/O traffic out. I do not want to be in VI doing 5-byte transfers when somebody else is trying to move a terabyte of data through the same disk drive. We'd like to split them out. IRIX has something called real-time partitions, real-time volumes. The whole purpose of that is to get my small I/O onto the data partition, the data subvolumes, and then move all my large sequential I/O to the real-time partition. For Cray people, we'd call that a secondary partition. Except in Cray, the operating system will determine whether you go onto the secondary partition, whereas in IRIX, the program has to be coded to know how to use the real-time partition. But they have the same conceptual concept, large sequential I/O. So those are some political issues that you have to deal with. And if you can't do it by software, then you get to simply cite policies. A lot of sites do not allow interactive access to the compute server, including database servers and web servers. Why can't you log into a database server and do what you want? Because then the database server cannot get predictable resources. I come in and do VI in a large file, and now the database engine doesn't have any memory to operate anymore. So a lot of sites do not allow interactive access into the server. And for a batch interface, that means submitting from my workstation into the origin. Now in this class, we're going to log into the origin and submit from there just for convenience. So I don't have to have you install NQE off on your workstations. Okay. But Chevron or some of these oil sites that Janet I know used to support, I'd get in there and one person would be mad that somebody else was doing text editing on a number cruncher. And they're saying, I'm trying to get my oil simulation, my oil reservoir simulation done, and you're writing hello mom. Okay. Those are policies. Do I allow interactive access or not? Now, up until 658, we had to enforce it by rules, simply saying, please don't do it. But we now have what's called User Limit Database, ULB, or ULD. The User Limit Database says a particular user can or cannot log in interactively. So my administrative support people could log interactive to debug things, but my batch users would not allow interactive access. So the User Limit Database allows me to control, on a per user ID basis, interactive and batch limits. And I could say you can log in interactive and use 50 seconds of CPU time, but if you want more than 50 seconds, you have to use a batch interface. And that's also one of the reasons I'm using NQE in this class, is because it supports User Limit Database right now, and none of the other products did. It also supports Cray accounting and supports Miser. That's the only reason I'm using NQE in this class right now are those three features: User Limit Database, CSA accounting, and Miser. Okay. If the other products were to support them, and I could get past the licensing, I would probably use PBS or something. Other site policies may also include file system policies. In my data center, we have temp and ptemp. Temp is scratch with a 1-day retention period, possibly scrubbed on reboots. Whereas ptemp is not designed for bandwidth, it's designed for large capacity files. So my data center ptemp has a 7-day retention period for your large files, and then it gets scrubbed. Home directories have backups on them so that you don't have to worry about retention periods. So when you're splitting out your file systems, you're often doing that based upon policies. And then you may, for example, put quotas on the home directory and say, I can't take more than 500 megabytes of data on this particular file system or something like that. But site policies are enforced by peer pressure. They're not enforced by software. Now to me, what the focus of this class is the word I'm going to use quite a bit this week called sizing. So as a system tuner, I've got to make size decisions. And I don't necessarily like the order here. Well, I do as an employee. I like to sell hardware. Buy more memory, buy more disks, buy more CPUs. Okay? But again, really, the first thing is to size the application first. So we're talking sizing. I want to make application decisions first. For example, memory sizes being affected by I/O buffers. When I use Nastran, Nastran has an argument on it to say how much scratch memory do you want. So if I'm on a small memory machine, I set it real small. If I'm on a big memory machine and it's important to me to run this Nastran, then I can up the memory, scratch memory of Nastran, and then it's got more scratch memory and less I/O. So it's not as much of an out-of-core solver. And most out-of-core solvers have that ability of saying how much scratch memory for the data that I'm reading in. So if I got Nastran as my most important application, I'm at General Motors, I'm vibrating these cars, I may get as much memory as possible and use as much of that memory for my applications. Okay. So that's an example of a sizing question. The other sizing question with the application might be the request size itself. If I'm moving a terabyte of data, I do not want to do it 1 byte at a time. I want to chunk up this data. Now here's a little clue, because I'm going to ask you this later. The friendly I/O request size for IRIX is 64 megabyte. I'm going to use the analogy later in the class about a fire bucket brigade. We've got all these buckets that we fill with water to put out the fire. We hand the bucket to the next person. The common bucket size within IRIX is 64 megabyte. So if I fill 64 megabyte into these fire buckets, I'm efficiently using the buffer space. If I do a 32 kbyte transfer, I'm going to waste half the memory. I'm still going to have a 64 kbyte buffer within memory, but only put 32 kbyte into it.
64K or 64 megs?
64K. If I said meg, I was wrong. I said meg. I got to listen to myself. Sorry. You're right. 64 kbyte is the friendly request size. How many people built striped file systems?
A lot.
What's the default step size?
128.
128 what? What are the units?
That's it's blocks now?
Yes, block is
It's blocks.
It's blocks.
quantity of
I think it's
So
blocks.
xcalc,
512
512 bytes to a block. So I'm going to take 128 times 512 bytes to a block, and I get 64 kbyte. So striping is defaulting to a 64 kbyte transfer. Okay, so this is what I mean by sizing. If I up my request size for Nastran and say let's do 64 kbyte transfers, that would be better for it. Or I can even up larger than that. If I go to real-time partitions, I can go larger request sizes and stuff. This is going to be a real important thing for us to understand. If I'm doing lots of little I/O, like credit card transactions, I can't get 64 kbyte worth of data on a credit card transaction. There's not that much information in there. So there I have to drop the size of the operating system down to match the application. But my first question is, can I up it in the application? I'd rather fix the application first. But if I can't, because of the nature of what I'm databasing, then I want to drop the sizes of what the file system can configured for it down to what that application is trying to do. So this word sizing, I'm going to be using quite a bit. But the first thing was to size the application. Okay? And I just gave an example using Nastran where I can affect request sizes and memory footprints. The second thing then for sizing is to size the OS. And this is usually system. Now, every operating system out there, when the developers release the operating system, they know they have to cover generic, middle of the road, safe for everybody. 64K byte was picked as a middle of the road. The video market would like it larger, the database market would like it smaller. Your job is to identify what direction you want to go. And PAR, for example, is going to give you your request sizes. So I look at my PAR data and say, it's 4K byte transfers. I talk to the developer and they say, well, we're databasing 4K byte records. I can't up that. I can't buffer more at a time. So then I got to drop things down. Okay, and with Systune, there's going to be a lot of parameters, particularly in file system buffer cache, that we can adjust. So what I'm trying to say is when I release an operating system, we pick a middle of the road that we think is safest for everybody. And then the system tuner's job is to profile and characterize what their particular site needs. I could have two Oracle database markets that are databasing two different things. I could have Oracle databasing email that's 1,000 byte standard text email. And I could have another one databasing video clips. Those are completely two different stories in terms of what I'm doing. Okay. So that's what I mean by characterizing my workload, figuring out, am I reading more than writing, writing more than reading, am I doing lots of little I/O, large sequential I/O. Now when you get into a university site, you're running everything. And that's where you get into the trade-offs and saying, okay, I'm doing lots of little I/O and a large sequential, I should, if they're important enough, create separate file systems for them. Otherwise, I'm saving money at the cost of performance by putting them into the same file system. There's always trade-offs. Okay. So OS tuning is really what we're focusing on this week, and being able to recognize what the application needs to be able to size it to that application. So the stripe request issue. If I took 10 disk drives and striped them 10 wide, that would be 10 times 64K byte. That would be the request size that my file system has been sized for or designed for. And if I'm doing 4 byte transfers into that 10 wide stripe group, I'm going to have very poor performance on it. The striping is not designed for lots of little I/O. It's designed for large sequential I/O. After the OS, then we've got our load level. And this is a batch interface. So with NQE, which is also NQS, PBS, and LSF, I can set up limits and say, I do not want more than one program that's over 1 gigabyte in size to run on my machine. Then the users have to declare how much CPU memory they need, and then the batch interface says, well, that's more than I have available, I'm going to hold you in a queue until the memory's there. Okay. There are other batch interfaces, I'm just listing the main three, NQS, PBS, and LSF. Another common one out there is called Kodi. That's very rare. And then the last thing we can size is the hardware. Of course, somewhere in here was expectations as well. I mean, when I went to Disney and they were complaining about their performance slowdowns, it was due to